a solution exists, and it can be easily be proved. So the idea of the phase plane, of the fact that you can plot x2 as a function of x1, is explained on this slide and equation number 9. Yeah, because actually this is why we can easily establish that the system locally has a solution. Okay, and the solution determines the trajectories of the system in the state space. Okay. And we had all these remarks. Oh, yeah, and an equilibrium point is actually a point, is exactly a point of coordinates x1 star and x2 star. Okay, that's an equilibrium point. So the equilibrium point is a point in R2. Okay, so this is x1 and this is x2. Okay, so this is R2. Okay. Right, and we can compute the equilibrium points just like we know the dynamics is 0, and we can also linearize. We can linearize, and linearizing around some desired equilibrium point yields a system of the errors, the dynamics of the very small errors, because the errors are very small. Okay. The dynamics of the deviations or the very small errors, and that's this system number 11, where O psi represent the higher order terms to be neglected. Okay, to be neglected, and you get this object psi dot is A psi. Again, this object is different from the original system. However, the behavior of this object around the origin, okay, determines what happens, what the nonlinear system is doing around the equilibrium point or the origin itself. Okay, it says here, yeah, psi dot is x. Psi is a different mathematical object than x dot is fx. Although psi is small, or actually very small, infinitesimal, I would say, it doesn't mean that the properties of the linear systems are automatically transmitted to the nonlinear one. That's the idea. Okay, that's the idea. Okay, it says here, so it's difficult to get rigorous results. Okay, however, in certain situations, especially when you talk about very, very small variations, the behavior of the linear system around the origin is very important to help us understand the behavior of the nonlinear system around the equilibrium point. And we've got results in this sense. Okay, especially for stability. Okay, and now we are going to prove that. How? We are going to essentially to study the behavior of the linear system around the origin. Okay, and we try to determine, to see how this is influencing, or what information we can extract about the behavior of the nonlinear system around the equilibrium point. Hence, we start with a linear system x dot is ax. This is a linear system with the initial condition x naught is x of 0. Okay, and the matrix A has this form, is a 2 by 2 real matrix. Okay, is a 2 by 2 real matrix. Right. From this guy, we can compute the solution of this guy. Yeah, separation of variables. That's not difficult to do. And using the definition of the matrix exponential, I just need to remind you that the matrix exponential e to the power at is identity plus at squared plus so on and so forth. This is the Taylor series expansion. Okay, so actually this is e to the power x for x equal at. Okay, this is the definition of the matrix exponential, right? And we are able to solve this system. Okay, so if you solve x dot is ax by separation of variables, you get the solution x equals a to the power at x naught, and here you just replace small a with capital A. Small a with capital A, and you get e to the power at x naught. Of course, this is not a proof. You can easily prove doing the same variation, separation of variables. Moreover, you can prove that e to the power at d to dt is actually a e to the power at. It can be easily proven. How? You just produce the derivative here, and then you take a as a common factor. Okay, you take a as a common factor. Okay, so for instance, if you do here, if you take the operator, okay, take the operator d to dt over this guy, okay, you get identity goes away, okay, because it's a constant. So you get a plus 2a. Oh, sorry. Here you get over like this. Okay, 2a over 2 at, so 2a squared t plus so on and so forth. Okay, so this is essentially 2 and 2 goes away. Okay, so this is essentially a times identity plus at plus so on and so forth. So this is, and this is e to the power at. So the proof is easy. Hence, you can easily do the integration. You can easily do the integration. So this essentially means that integration e to the power at is e to the power at. That makes sense. Okay, plus whatever constant. Yeah. So you can easily prove that. If you can prove that, then you can prove that the solution of this differential equation is xt is exponential of at times the initial condition x naught. Right. And now the discussion is, how is xt behaving? How is xt behaving depending on how a looks like? Because this is determined. So one other property we have is that if you apply a coordinate change of this form to the matrix A, then this change of coordinates, it can be also applied to the matrix exponential. Okay, and now we discuss several cases occurring depending on the type of matrix A. First of all, consider that the matrix A is non-singular, so it's invertible, hence its determinant is non-zero. Okay, in this case, the unique equilibrium point of x dot is ax is the origin. Okay, is the origin. So 0 is the unique equilibrium point of the system. Okay, and of course, since the determinant is non-zero, a has only eigenvalues different from 0. Okay, different from 0. Right. We are interested in the eigenvalues of the matrix A. Okay, in the eigenvalues of the matrix A. Okay, because the eigenvalues determine the behavior. That's the idea. The eigenvalues are going to determine the behavior, and we are going to exploit all the properties of linear dynamical systems. First of all, how are you going to characterize the eigenvalues of a matrix? Yeah, let's do a little bit of recap. Okay, so let A be an n by n real matrix. Okay, or it can also be complex. You don't need you won't need it real. So let A be a complex matrix. Okay. Okay. Definition. Lambda in the complex number lambda is an eigenvalue of A, that is I dot E dot lambda belongs to the spectrum of A, or lambda of A. It depends on how you denote this. If and only if there exists V in Cn, V non-zero, such that lambda I minus AV equals 0. V is called the eigenvector associated with the eigenvalue lambda. Okay? Hence, when is this zero? When is this zero? Okay, so the first result, it says that lambda is, or lambda is an eigenvalue of the matrix A if and only if determinant of lambda I minus A is zero. Yeah, it's a straightforward corollary of the definition. Okay, of the definition. Yeah. Okay. So the eigenvalues, that means, is equivalent to saying that the spectrum of the matrix A is the set of roots of the polynomial PA lambda that lambda I minus A. This is called the minimal or the characteristic polynomial of the matrix A. We talk about non-derogatory matrices where the minimal and the characteristic polynomial are one and the same thing. Now, a special case is n equal to, which means that we have the first result that PA lambda, this polynomial, is actually lambda squared minus trace of A lambda plus determinant of A. Okay, plus the determinant of A, where trace of A is A11 plus A1 plus A22 is the sum of the diagonal elements. Okay, so for n equal 2, we get A equal A11, A12, A21, A22. Okay, and in this case, this is the trace, and the determinant of A is this guy. Okay, and is this guy, A11, A22 minus A12, A21. Okay, we know that. Yeah? Right. What else? Oh, and finally, we have the very nice result that's the Hamilton-Cayley theorem, stating that PA of A is zero times n times n. Okay, this is the Hamilton-Cayley theorem, which is one of the most wonderful mathematical results, saying that an algebraic equation is verified by a matrix. Yeah, by a matrix. So this is a recap about eigenvalues, characteristic polynomial, and all these things for second-order matrices. Okay? But things are general. And in general, just remember this. Yeah? PA lambda for any matrix is lambda to the power n minus. So it's always the second coefficient of the characteristic polynomial is the trace of the matrix. And then I don't know, but I'll always know that the last coefficient, it's always the determinant of A. That's what I always know. Okay. Please keep in mind that also trace of A, this is from Viet's relations. one more thing, that the trace of A is always the sum of all eigenvalues. It's always like that. You can easily prove this. Okay. So these are some matrix facts. I'm not sure whether you're familiar with these things or not, but I think it was my duty to help you recall this stuff. Okay. So what happens now? We have this second order matrix, okay, with the eigenvalues lambda1 and lambda2. As I said, they are the roots of the characteristic equation lambda squared minus trace of A lambda plus determinant of A is 0, where this is the trace. This is the trace, okay, exactly what I said earlier. Now, you can easily, since A is, you can make it diagonal or bring it in some special Jordan form, okay? So essentially, you don't know. Any matrix A is T, I don't know, J1, JL, where these are Jordan blocks. These are Jordan blocks, okay? Sorry, one. Okay? These are Jordan blocks. You can always write that. Okay? This is a Jordan block with for eigenvalue A, lambda I, eigenvalue of multiplicity. So this is the most general case. Multiplicity mu I. Okay? So this Ji has the dimension mu I. Okay? And sum of mu I equal 1 to L, is the whole dimension of the matrix N. Okay, so let's recall that. So essentially, any matrix can be written in this form depending on its own eigenvalues. Okay, and this is the most general form of it. Okay, you can always do that. So let's do this ourselves. We can apply a coordinate transformation. Yeah, here I forgot to mention T invertible. Yeah, so there exists a T invertible such that this is possible. Yeah, and you know we've got algorithms to determine the matrix T. Okay, let's come back to our special case. So we have a coordinate transformation Z equal Tx with T and T inverse 2 2x2 matrices, transforming the system 13 into 15. How do you do that? Okay, so Z equals Tx. You apply the time derivative and you get Z dot. T is a constant matrix, is Tx dot. Okay, but this is x dot is Ax, is T Ax. Now from this one we get x equal T inverse Z. So this is T inverse Z, and you may call this A hat. Okay. All right. This is what happens here. This is what happens here. Okay. Transforming 13 into this guy 15. Note that also the coordinate change is also applying to the initial condition. Okay. So the initial condition is also transformed into from x naught to z naught. Okay. So you get this system, but this system is in Jordan canonical form. And now we have special cases. We have some situations which might occur. We can have real simple or multiple eigenvalues. Real simple or multiple eigenvalues. Okay. For instance, this is the diagonal case. This is the diagonal case when the eigenvalues are distinct. This is the Jordan block case when you have one eigenvalue of multiplicity 2, yeah, lambda is an eigenvalue of mu multiplicity 2, and you may have the complex conjugated values where you can have the special form where sigma, yeah, it's complex conjugated values. So lambda I is lambda 1, 2 actually, because I is 1 and 2. Yeah? Lambda 1, not I. Lambda 1, 2 is sigma plus minus j omega. Okay? And it's the eigenvalues of this guy. These are the eigenvalues of this guy. Okay? It's easy to prove. It's easy to prove, yeah? When you do that lambda I minus a, and you take the simple determinant, you can easily, and actually, you know, yeah, lambda square minus 2 sigma lambda plus sigma square plus omega square, okay? Right? And this is the sum. 2 lambda is lambda 1 plus lambda 2. And this is lambda 1, lambda 2. Okay, so it's easy to prove. And this is the canonical form when you have complex conjugated values. Okay. Please, if you have any questions, just stop me and ask. Any questions about this metric stuff? Or are you familiar with all this?
It is clear until now.
Okay, fine. If you feel like everything's falling into place, then I'm fine. All right, so you have the transformed system. Z dot is a hat z. What's the solution of this guy? Is e to the power a hat t z naught. This is clear, okay? Well, so what are we going to investigate? We are going to investigate each situation. So we are going to replace a hat with all these situations. This. We also have these are non-derogatory, non-degenerate situations, okay? But we can also have the degenerate situations. A equal lambda 0, 0 lambda. This is a degenerate situation. And lambda is 0, 0, 0, 0. This is another degenerate situation. Not lambda, a, sorry. Okay, so we are going to investigate all the possible occurrences of A. Okay, degenerate or non-degenerate, right? Okay, so we are going to investigate each of the situations above to understand the behavior around the origin equilibrium point. Okay. Okay, so using, it says here, using the right coordinate transformation, we can simplify our analysis. We can understand things more clearly. First case, when we have real eigenvalues, we've got real eigenvalues, okay? That means that the determinant of the, I remind you that the characteristic equation is lambda squared minus trace A lambda plus det A equals 0. So first case, and delta is always B squared, so is trace of A squared minus 4AC, yeah, for det A, okay? So this is the discriminant of the second order equation, algebraic equation, okay? So now if delta is positive, then we know that the second order algebraic equation has two distinct real roots, okay? Two distinct real roots, okay? So we have, in this case, two distinct real roots, lambda 1 different from lambda 2, real. Okay, and you can write. Okay, that means that z is exponential of lambda 1, 0, 0, lambda 2, t, x, z naught. Okay, so this is what? This is not what? The exponential of this guy is very simple to compute. It's very simple to compute. You can prove that by ourselves using the definition of the matrix exponential. So this is exponential of lambda 1t, 0, 0, exponential of lambda 2t, times z01, z02. Let's split the initial condition in two coordinates. Okay? Okay, so you get z1 dot is e lambda 1 t z1 0 or z1 0, sorry, 1 0 and 2 0. Okay, and z2 dot is e lambda 2 t z2 z2 naught. Okay, all right. What's the next step? Now we are trying to prove, to see what goes on in the phase plane. So what goes on in this plane, z1, z2 versus z1. We try to understand what happens in the trajectory space. Okay. So how are we going to do it? How are we going to do it? We are going to extract an exponential. We are going to extract an exponential. Okay, and substitute it in the second one. Okay, so from the first equation, you get what? From the first equation, you get that e lambda 1 t is z10 over z1. Yeah?
I think the other way around.
The other way around. You take it from the z2. That's what you mean?
I mean z1 over z1 0.
Oh, z1 over, sorry. Yeah, I was wrong. You're right. E lambda 1 t is z1 over z1 0. So that means what? That t is logarithm z1 over z1 naught 1 over lambda 1, right? Natural logarithm. You agree? And this further means that when you take the exponential once again, e, so you substitute this by, you multiply this with lambda 2, and then you have e lambda 2t is what? Is what? E, no, is hmm? No, actually you can take this, you can write this guy, you can put it inside and say to the power 1, right? You agree? You agree, huh?
Yeah.
So this is z1 over z1 0 to the power lambda 2 over lambda 1. You agree? You agree. Yeah, and you substitute this and you get formula from this 17 comes up. Okay, from this simple computation you get 17. So you can write the z2 like z1, okay, with this constant c. with this constant c. Okay, right? So essentially, depending on if lambda 2 is larger than lambda 1 or lambda 2 is smaller than lambda 1, okay, you can have different types of trajectories. So we split into other cases now. And the first case is when the determinant is positive. So both eigenvalues have the same sign. Determinant is positive means both eigenvalues have identical sign. And we assume that lambda 2 is smaller than lambda 1 and negative. We assume this. Hence, what happens? If lambda 2 is smaller than lambda 1, then lambda 2 over lambda 1 is less than 1. Hence, when you take t to infinity, z1 goes to 0 when you take t to infinity, because you have this property. Okay? Hence, lambda 1 is called the slow eigenvalue, and lambda 2, which is more to the left. So if you look at the complex plane, this is lambda 1, this is lambda 2. This one is going closer to infinity, and this one is going closer to 0. Hence, this is the slow eigenvalue, and the lambda 2 is the fast eigenvalue, because the exponential goes to 0 faster if the eigenvalue is further to the left. Okay? Okay, so z1 converges to 0 slower than z2. That's the idea. That's the idea. Accordingly, they say here the eigenvectors associated to lambda 1 and lambda 2, they are going to be the slow and the fast eigenvector, respectively. Okay? So we are going to do this combination. Now, the slope of the curve, because we are trying to draw something. Okay? So we are doing a little bit of geometry, and we can compute the slope of the curve defined by 17. Defined by 17. What is the slope? It's the derivative of z2 with respect to z1. I remind you, we need to make a function, z2 versus z1. And if you want the slope, you have to take the derivative. This is how you compute the slope. Okay? This is how you compute the slope. And the slope is given by this formula. By this formula. And now, look, lambda 2 is larger than lambda 1. Hence, lambda 2 over lambda 1, lambda 2 over lambda 1. Oh, sorry, this is larger than 1. Why didn't you tell me? This is larger than 1. Sorry. True? Oh, no. No, I was right, right? Yeah, but they have the same sign. So if you take in absolute value, no, this is true. It's true. It's like this. It's like this. Okay? It's like this. Yeah? At least you can do it like this. Okay. Fine. So the slope. Okay. You have lambda 2. Lambda 2. Oh, lambda 2 over lambda 1 is larger than 1. Okay. Fine. So this is the slope, and then what you have, m goes to 0 when z1 goes to 0, and m goes to infinity, indeed, when z1 goes to infinity. So for small z1, they say here, the arctangent of m is almost 0, and the trajectories are tangent to the z1 axis, the slow eigenvector. Okay, and for the large one, you have pi over 2, so essentially you get something like this. Okay, and the trajectories become parallel to the z2 fast eigenvector. Okay, so what you actually have, if you look at the analysis, you can draw this. Okay, you can draw this. This is you can draw. So you have what's called, so your equilibrium point is a stable node. Please note that the axes Z1 and Z2 are invariant sets. Okay, they correspond to the eigenspaces associated with lambda1 and lambda2. They determine the eigenvalues. Okay, so this is a stable node. Your equilibrium point is a stable node in this case. It's stable because this is how things go, because the lambdas are negative. So this is a stable node. Okay, all right. Now, of course, if you go back to your original system, x dot is ax, then the eigenvectors become skewed. Of course, become skewed because this is canonical. This is canonical reference, and this is not canonical. This is the original. This is not canonical. Okay, this is the original, and this is a stable node. This is okay. This is the direction. This is the direction. So coming back to the initial coordinate system, returning to the initial curves are going to change their shape, of course. Okay, but not the topological character. So they look the same. They are still a node. The trajectories approach asymptotically the origin, tangent to the slow vector, and parallel to the fast direction. Parallel to the fast direction, of course. Now, what happens in this case? What's changing? Do you think this figure 3 is changing, or only something in figure 3 is changing? What's your opinion about this? Hmm? What's changing? Hmm? What's your opinion? What's changing? Okay. Don't pick the apple. Right, have you found the answer to my question? What changes? Hmm? Yes.
For
I'm listening.
instance, the slope is going to be smaller.
Not necessarily. What changes is this. It's going to be unstable now. Yeah? We know that a linear system, yeah? So remember, recall, a linear system, a linear dynamical system, okay? System is stable, well, asymptotically actually stable, if and only if the spectrum of the matrix A is included in the left complex half plane, okay? And if an eigenvalue has a real, yeah, this is equivalent to saying that the real part of the eigenvalues is negative for all eigenvalues. Okay. Now, if it's unstable, then the real part of the eigenvalue, so in this case it's real, is positive, then the system is unstable. Okay, it's very easy because e exponential to lambda I t is 0 when t, no, let's say it like this. Let's say it like this. If lambda I is minus sigma I plus minus j omega I, with sigma I positive, okay, then exponential of sigma I plus of lambda it, exponential of lambda it, which is exponential of minus sigma it times exponential of minus j omega it. Okay? This goes to 0 when t goes to infinity, and this is just bounded. So it all goes to 0 when t goes to infinity. Okay? Okay? But if this is positive, lambda I is sigma I plus minus j omega I, then e to the power lambda it goes to infinity when t goes to infinity, because it's infinity times bounded. Okay? So it goes to infinity, that's why. So if this happens, change, okay? It's an unstable node. It's an unstable node, okay? And that's what it says here. If this happens, okay? Well, whatever. The shape of the trajectory isn't changing, okay? The sense of the motion sense, okay? The direction of the motion along the trajectory is changing, okay? Because this happens, okay? In this case, we have an unstable node, okay? So unstable, okay? So this is unstable, and this is stable, okay? Is it clear now?
Yes.
Right. Now, what happens if the eigenvalues have an opposite sign? If the eigenvalues have an opposite sign, that means this situation. Okay? So in this situation, it's still unstable because one of the eigenvalues is positive. It's still unstable, but the shape is changing. The shape is changing. And so now, if you go back to equation 16, whatever equation 16, this equation 16, okay? Okay, so one is going to 0 and the other one is going to infinity. One is going to 0, whereas the other one is going to infinity. Okay, z1 goes to 0 and z2 is plus minus infinity. So this type of equilibrium point, this is an equilibrium point which is called saddle point. I'm not sure if you have here, saddle point, okay? This is a saddle point because z2 goes to infinity and z1 goes to 0. So it's different from the node. Okay, the node is like this. Okay, well, saddle point, these are turning their backs. It's like this. Okay, it's like this. Okay, node versus saddle point. And of course, saddle point means instability. The equilibrium point is not stable. Okay. Right. Now, what happens if we have a double real root? We may have the Jordan block case, which is the normal, regular, physical, so to speak, real case, and we have the so-called degenerate case, which is this one. And we can treat this in a similar manner. Okay, so we have what we have. Z1 dot is lambda z1 plus z2. Z2 dot is lambda z2. Okay, and you can do all the computations now. So here you get z2 is e lambda t z2 0. Okay, and you substitute it here. So this is lambda 1 plus z2 plus e to the power lambda t, lambda 1 z1, sorry, lambda 1 okay, lambda 1 z1 plus e to the power lambda t z2 naught. Okay, and you can, sorry, okay, you can do some computations, okay, because you can extract t here to be 1 over lambda, so you can have this again. It's a natural logarithm z2 0 to the power 1 over lambda, okay? And how to compute the first one? Yeah. Well, there's different ways to do that. For instance, my view of these things is I could apply the Laplace transform over this guy. I'm not sure whether this is so this is further lambda 1 z1, and then you get here what? Z2 plus, and you substitute this into this one, okay? And then you get e to the power lambda t equal what? Z2 over Z2 0, right? You agree? You agree, huh? Yeah, that's good. Because you just put lambda here, yeah. So then Z1 dot is lambda 1 Z1 plus oh, but if you, this is Z2, but I already know that. So I was trying to just substitute this, but we already know that. However, what you can actually do, so like I said, you can apply the Laplace transform on this guy. And when you do the computations, you get that Z1 is Z2, you get it the other way around. Z2 times Z1 naught over Z2 naught, you can do the computations yourselves, plus 1 over lambda logarithm Z2 naught. Okay, Z2 naught. Yeah. And you can compute the slope, and you can do other things. I can give you the proof of all this in some notes I have. I have some notes. Let's see if we can add these notes to your lecture. Okay, class notebook. I have some notes where I can show you all this. Yeah, because I don't have to do all the computations from scratch. Yeah. Just bear with me a minute so I can find the notes and I can upload them to your class notebook. Just a second. File. Right. Seminar. Chapter 3. But why am I making a new page? No, I shouldn't be doing that. I just should do this. At the end of the lecture, I'm going to add the notes. That's here. There you go. Oh, well, I hope you do not mind, because these are again in Romanian, but these are the formula. Okay, I'm going to show you in a minute. Page. Delete page. Right. Okay, so if you go back to the end of the lecture, you see here, you can see my screen, right? So here we have some solved problems. Yeah. Look, you see, if you have a Jordan block, these are the computation I was talking to you about earlier. Okay, I was talking to you about earlier. So this is how to extract the time, and then you apply the Laplace transform for Z1, and then you get this equation for Z1. Okay, and you substitute, you compute the solution Z1. You compute the solution Z1, and finally you get that Z1 has this sort of dependency, okay? This function of Z2. So it's Z1 as a function of Z2. That's not an issue, because you can easily get Z2 as a function of Z1, okay? But then you can also compute the slope. You can also compute the slope, and you realize that the slope as Z2 goes to 0, the slope goes to infinity. And then you get this shape. Get this shape of the trajectories. You get this shape of the trajectories for this case. Okay, this shape. So when you have two eigenvalues in a Jordan block, you can also do the case when you have lambda 0, 0, lambda. Okay, so these are just lines. Okay, these are just lines. And then you also have the case when you have one eigenvalue and the rest is 0. So these are parallel lines like this. Okay, it's a drawing like this. So going back to this. Okay, going back to this. Okay, so in this case, you have something like this. Okay, or like this. Okay, and if lambda is positive, then if lambda, sorry, is negative, it's stable. If lambda is positive, this is unstable. Okay, and this case, so here you get for when a hat is lambda 0, 0, oh, sorry, is lambda 0, 0, lambda. When you have this case, then Z1 dot, okay, is lambda Z1, Z2 dot is lambda Z2, So Z1 equals Z2. Actually, they're not equal. Z1 is E lambda T Z1 naught. Z2 is E lambda T Z2 naught. Okay, so you get E to lambda T here is Z2 over Z2 naught. Hence, Z1, or from here, yeah, you get Z1, no, E lambda T. E lambda T is Z1 over Z1 naught. Then you get Z2. You get Z2 equal Z1 times Z2 naught over Z1 naught. Okay? So what have you got in this case? You've got lines. Lines with a slope Z2 naught over Z1 naught. You've got lines, and you've got stable or unstable, okay, in this case. Yeah? Okay. So now we can move on to the more important cases. We can move on to the more important cases. And we go now to the very important case of stable or unstable complex conjugated eigenvalues. Complex conjugated eigenvalues. Okay. So if the determinant is negative, then the two eigenvalues of A are complex conjugated pairs like this one. With sigma real part, and the trace of A is 2 sigma, and the determinant of A, as I showed earlier, is sigma squared plus omega squared. Okay. Right. The equivalent, they say here, real system, because you see this matrix is real with complex eigenvalues. That's why we use this canonical form, because this is the real canonical form of the complex eigenvalues. Because otherwise, if you just do diagonalization, you could have A tilde is sigma you could have here sigma plus j omega, and here sigma minus j omega. But this is not good because this is a complex matrix. So I don't want to do that. That's why I'm using this real canonical form for complex eigenvalues. And the resulting canonical system is this one. Z dot is sigma Z1 minus omega Z2. And here on the second line, you get Z2 dot is sigma Z2 plus omega Z1. This is the real canonical system. Now, how can we treat this guy? How can we solve this guy? That's the question. What are we going to do now? Now, because this is essentially, if you look at the matrix, this is a rotation matrix. If you're familiar from numerical methods or matrix theory, this is a rotation matrix. Okay. We should go to some rotational coordinates. We go to the so-called polar coordinates. And you apply this nonlinear coordinate transformation. So after the linear coordinate transformation, you apply a nonlinear coordinate transformation. This is a nonlinear coordinate transformation. Nonlinear coordinate transformation. Okay. Essentially, z equals phi x, so to speak. Okay, this is nonlinear, a nonlinear coordinate transformation. Now, who is the so it's r cos theta, z2 is r sine theta. Who's r? R is the radius, so is the square root of z1 square plus z2 square, and theta is the angle between the two phasors. These are phasors now. Is the angle between them, is this arctangent. Okay. Hence, for initial condition, you get this, and you get this for the initial conditions. And now you apply the coordinate transformations. Okay. So you get z1 dot is r dot cos theta plus r, and actually we can apply the derivative now, minus minus r sine theta. And this is, okay, r sine theta. And furthermore, z2 dot is r dot sine theta plus r cos theta. And this is each of them, you substitute now these coordinate transformation into this guy on the right hand terms. So this is sigma r cos theta minus omega r sine theta, and then you get omega r cos theta minus sigma r, this is r sine theta. Yeah. Oh yeah, and here I made a mistake, no one told me. Times theta dot. Times theta dot. True? You agree, right? Yeah? So what do you do now when you do these computations? Essentially, from this equation, you have to get r dot and theta dot. You have to get r dot and theta dot. And how do you do that? You just do multiplications. So here you multiply. You multiply with, for instance, to get r. If you want to get r, you want to get rid of the, you multiply this with cos. So first you do, so let's do this equation 1, and this is equation 2, or let's make it a and b, or I. And this is equation I, and this is equation double I. Okay, so essentially what you do now, you do I multiplied with cos theta plus double I multiplied with sin theta, sine theta. Okay, you do this operation. And this is equivalent to r dot times cos square theta plus sine square theta, but this is 1. Okay, you see? Is equals. You multiply the first one by cos. So sigma r sine theta cos theta minus omega r sine square theta. True? Plus, because you have to add the second term, plus omega r cos square theta minus sigma r sine theta cos theta. You see? So these are computations of the coordinate of the nonlinear coordinate transformation. This term goes away with this term, and these two terms are added, and they're actually there is a mistake somewhere. There's a mistake somewhere. So this goes away. This one. Because you should also get against sine square plus cos square, because essentially you get this equation. You know? But I made a mistake somewhere. So you multiply the first one using cos. Oh yeah, so it's sigma r cos squared. I made a mistake. It's sigma r cos squared. Sorry about that. Cos squared. And this is sigma r. And it's not minus, it's plus actually. Sigma r sine squared. Sorry about that. I made a mistake. Yeah. And this is sin cos, sin cos. Made a mistake. Okay, and this term goes away, and then you get sigma r. Okay, and you get the first equation. Identically, you compute the second equation, so you get this very simple linear system in polar coordinates. What's the solution of such a system? This is the solution of the radius r, and note that this is a linear equation, is a linear function of time. Is a linear function of time. Eliminating the variable t from these equalities, you get this simple equation number 18. Okay, so essentially you get here t equal theta minus theta 0 over omega. I think this is the reason, or not? Or how do you eliminate t? Yeah, because you have to substitute it in the first one. So exponential, yeah, you get the exponential. So then r t equals r naught exponential of sigma over omega times theta minus theta 0. But where's theta minus theta 0 times theta? Where is theta 0 going away? Hmm? Oh, and it's a constant times, and you take this one and you put it in a constant. Yeah, so you get r0 e to the power minus sigma over omega theta 0. So this is the constant c, yeah, times exponential of sigma over omega theta. Okay, now it's clear. Indeed. So you get this variation. Okay, you get this variation for your radius, for your radial coordinate. This variation. Okay. Again, keep in mind that theta is a linear function of the time with the slope omega. So the curve defined by 18, it says here, is called the logarithmic spiral, and the corresponding equilibrium is called a focus. It's a focus. Yeah. Why? Because theta, okay, is a linear function of time, and this exponential is growing or decreasing. This exponential is growing or decreasing. Okay, so this is a logarithmic spiral. So essentially, you have to get something like this. Something like this. Okay, you see? Focus. It's called a focus. Now, if you go back to the original coordinates in the Cartesian system, okay, go back, you notice that the general solution, now you go back, okay, z1 and z2, okay, so z1, yeah, is r cos theta, right? So it's r0 e to the power sigma theta, we substitute this, okay? And then you can write something like this, okay? So Z1 and Z2, yeah, are like this. Now, if sigma is negative, then the spiral goes like this. But if sigma is positive, it's the other way around. So stable and unstable focus. Stable, this is a stable focus. And this is an unstable focus. An unstable focus. And then you also have this configuration when sigma is 0. So this is essentially, imagine that sigma is 0. If sigma is 0, the radius is a constant. If sigma is 0, r theta is a constant. R theta is a constant. And theta keeps, the angle keeps linearly evolving. Yeah, it has a linear dependence on time. So then you get this situation. This is undecidable because you don't know what to do with this. You don't know whether you have stability or you have not stability. The question is, from a physical, from an engineering point of view, is this a stable structure? Question. Is this a stable structure? Is this a stable structure? So do you keep this circle for a long time? Can you keep it? What do you think? What's your opinion about this? What's your opinion about this?
Maybe bounded input, bounded output stability.
No, you can't say anything because if you remember correctly, when you have stability on the when you have eigenvalues on the imaginary axis, you're almost unstable actually, because you get oscillations in time. You agree? My question is this? I'm not talking about the stability of the equilibrium point. I'm asking about the stability of such a circle. Do you think this circle configuration can be kept for a long time and in any condition? So is this robust or not robust? Let me ask you like this. I mean, do you think that this circle can easily become, for instance, a focus, unstable or unstable focus? Can you have this situation? That's my question. Well, this structure of a center is not stable because sigma equal to 0 is a mathematical assumption, not an engineering assumption. Imagine that sigma equals epsilon, very, very small, but positive. It becomes unstable, or negative. It becomes stable, right? You want to say something?
No, sorry.
Okay. You agree? So this sigma equal to 0, this assumption, this is not real from a physical point of view. Okay? It's unstable. So it's not, we call this configuration, and we'll explain this a little bit later. This is not structurally structurally stable. This is not structurally stable, okay? Yeah. But we'll discuss this a little bit later. Now, can you imagine what's the case, for instance, physical case, when you can achieve such a configuration of a center? Imagine, for instance, the pendulum or the mechanical oscillator. To what is there corresponding this case with a zero real part for the eigenvalues? Can you imagine? What physical configuration is this corresponding to? Sigma equal to 0. When you have no what?
Dynamical response.
No, you have a dynamical response. On the contrary, way too dynamical. You haven't got what? Think about it. Think about the mechanical oscillator, or think about the pendulum. What's bringing the pendulum back to the equilibrium point when you swing it? What's stopping it? What's stopping the gravitational pendulum? What's bringing it back into rest? What's resting the gravitational pendulum? So the gravitational pendulum is hanging and it's swinging. So what's resting? What's putting this guy to rest? What's killing the motion of the pendulum? Can you imagine? So if the pendulum is swinging and you let it swing, what's bringing it back to the resting point, to the zero equilibrium? Why is the motion stopping?
Due to forces of gravity and friction.
No, the friction, not the gravity. The gravity is swinging. Okay, but when you have the friction, due to the viscous friction with the air, the pendulum is stopping. So sigma equal to 0 to which case is corresponding? The pendulum is swinging forever. When you have no?
I would say friction. So
Yeah, when you have no friction. So this is a no friction case, exactly. A no friction case, exactly. A no friction case. True? But this is not real. This is not real because there's always a little bit of friction. Not friction you can only have in ideal environments, right? True? So always, that's why it's not structurally stable. It's not structurally stable, okay? Because you can always get a little bit infinitesimal friction, okay? And this configuration doesn't hold any longer. That's why linear systems are not good oscillators. That's why if you need an oscillator for electronics, for instance, you go to the van der Pol oscillator, because no matter what you do, it will always oscillate, no matter how you perturb that. If you perturb this guy and sigma becomes non-zero, you can get it stable or unstable. But a van der Pol oscillator, for instance, or a nonlinear oscillator, it will always oscillate no matter how bad you apply, how badly a perturbation changes the system or affects such a system. Is it clear what do you understand what I'm saying? You understand?
Yeah.
Yep. Okay. Right. Would you agree for a 5-minute break and then we carry on?
Sure.
Okay. Let's have a 5-minute break and let's go on. Okay, at 4:30. Okay, I'm back. Right. Where's my pen? Are you still here? Right.
Yes.
Additional cases. More splitting hairs. Okay. We have to go into detail because we have many possibilities, many situations. And it's nice to go through all of it. Okay. Now, we talk about the cases with respect to the trace, okay? Trace of a negative, trace of a positive, and trace of a zero. Trace of a zero, this is equivalent to sigma equal to 0 case. The real part of the eigenvalues or both eigenvalues are 0, okay? Right. Well, if sigma is negative, okay, because we talk about complex conjugated eigenvalues, meaning the trace of A is 0, then Z1 goes to 0 and Z goes to 0, and this is stable focus. Okay, so sigma negative, stable focus. Okay, on the contrary, they say here, if sigma is positive, the sense of motion is reversed. So both now go to infinity as time goes to infinity. Hence, sigma positive is an unstable focus. Okay. In this case, the focus is unstable. So focus is stable, focus is unstable. Finally, let's talk about the case which we have already mentioned. Trace of A equal to 0, hence sigma equal to 0. That means A has got two eigenvalues on the imaginary axis. Okay, so it's this case. This is im, this is real, minus omega, yeah? This is the j omega axis. Yeah. Well, in this case, the solutions are harmonic. Sigma goes to 0, and then the solutions, if you look here, you have in this place you had these terms. These terms meant that the oscillations are going to be amplified, or how do you call that? Amplified, or how do you say this in English?
Dampened.
Sorry?
Like this, dampened. I don't know.
Or damped, exactly. Amplified or damped. Amplified, very good, thanks. Or damped, exactly, very nice. Now, in this case, there is no damping, no amplification. Hence, it's constant. R0 is constant. The only one that's changing is the omega t. The omega t implies that you have a constantly rotating phasor. So you have this guy with a constant radius, and it's going to rotate on and on and on and on. Okay? This is the radius, which is constant, and the trajectories are going to stay on the circle like this one. So z1 squared plus z2 squared is r0 squared. Okay, r0 squared. This is the center. The center we mentioned earlier. Okay, the center we mentioned earlier. So in polar coordinates, this exponential, okay, turns everything into a focus. This exponential term, a stable or an unstable focus. Whereas in this case, when sigma is 0, everything is a center. Okay? All right. So now you go back to the Cartesian. No, sorry. You go back to the original states X. You go back to the original states X. And you realize that this is constant. So this is the energy. The energy when sigma is 0 is constant. So it makes sense. Constant energy, constant oscillations, center. Okay? Let's look at the pendulum. The pendulum energy is this one. Okay? So the amplitude of the oscillations depends on the initial state of the system. Okay? And here it says the linear oscillator is not robust because its structure gets lost, being exposed to any arbitrarily small perturbations, okay? Like this one as well, Now, can we talk about structurally stable equilibrium points? This is the question. Of course, the node and the focus and the saddle point, okay? These have a stable structure, so no matter how you perturb them, they stay the same. No matter which disturbance is disturbing these equilibrium points, they keep the same form, they keep the same shape. Their shape is invariant with respect to disturbances. Whereas the center, this guy is not structurally stable. Okay, so the idea is, of course, this is related to this energy discussion. It's related to this energy discussion as well. Okay. Well, structurally stable equilibrium points. Okay, structurally stable equilibrium points defined by strict inequalities, stable or unstable, a node, a saddle point, or a focus. Stable or unstable nodes, saddle point, which is unstable, of course, by default, and stable or unstable focus. The center, however, as we said before, is not structurally stable. Okay. Neither are stable or unstable the nodes defined by multiple eigenvalues. Okay. Why? Because there's always a difference that might appear between the two eigenvalues. Okay. For instance, consider the matrix A singular. Its determinant is 0. 0 is not the only. So the second case. Okay. If A is singular. If A is singular, this means that one of the eigenvalues of matrix A is 0. Okay, we remember that the determinant, this is λ1 times λ2. That means there exists λi equal to 0. This is what it means. Okay. Well, in this case, 0, of course, for x dot equals ax. So in this case, if det A is 0, when you solve the equilibrium equation ax equal to 0, since this is no longer invertible, you might come across an infinity of solutions. Okay, so any vector corresponding to the 0 eigenvalue is an equilibrium point. Okay, so there exists x non-zero such that ax equal to 0. Okay, so 0 in this case is not the only equilibrium point any longer. Assuming that one of the eigenvalues is 0 and the other one is non-zero, the other one equals trace of A. Okay. Then in the canonical form for the Z system, one equation is like this. So one equation has a constant trajectory, whereas the other equation has a dynamic evolution. And the equilibria points are of this type. The equilibrium points are of this type. Okay. All right. Right. The situation they say here when lambda equal to 0 is a double root of the characteristic polynomial, this is a completely degenerate situation, a completely degenerate situation. Well, if you have 0, a double eigenvalue in a Jordan block, this is all right. This is all right. Okay, because this is what? This is essentially lambda squared equal lambda squared. Yeah, the characteristic polynomial is lambda squared here. Lambda squared. Okay, this is the characteristic polynomial in this case. So this is rather okay, although this is also in the limit okay. Okay, but you may also have this degenerate situation. This is completely degenerate. Okay, and of course, it only makes sense that the more degenerate the situation is, the less robust it is. So subject to any perturbation or to any disturbance, these lose their structure. These matrices lose their structure. Okay. For instance, yeah, all these cases you can plot. You can plot the and we can do this exercise. We can plot these the phase portraits of such equations. Okay, let's see if we can do this in MATLAB and see how they look like. Let's try and look at this. And see if we can get something out of it. I'm just trying to start my MATLAB on the desktop computer so we can do the simulations, okay? Just hold on a second, please. It'll start any minute now. Come on. Right. Now, if you look, let's just talk a little bit about this situation. So, if we have a perturbed system, okay, we add a delta to the matrix A, okay, and you get this perturbed system where delta has arbitrarily small elements, okay. The eigenvalues of a matrix continuously depend on the elements. That's a fact, okay. So for every epsilon positive, there exists a delta epsilon positive, such that if the variations in parameters are less than delta epsilon, then the eigenvalues, they say here, of this matrix belongs to an open ball of radius epsilon centered around the eigenvalues of A. So any disturbance delta A introduced into the system x dot is AX changes the modes, the eigenvalues, you see, changes the eigenvalues into a ball. Hold on a second. Yeah, so the disturbances introduce this, change the eigenvalues into a specific ball, such as figure 7 shows. Okay, look at this. So now, if you're on the imaginary axis, in this case, this is the center case. This is the center case. Any small perturbation is bringing the eigenvalues either here, where you get a stable focus, or to the other side, where you get an unstable focus. That's why we call the center not to be structurally stable. Not to be structurally stable. Okay? Is the argument clear to you? Why the center is not a structurally stable equilibrium point? Okay, the MATLAB has started. Let's see if we can change the share screen. The share screen has changed. Hold on a second. All right. Let's open some programs for this lecture. Some M files. Non-linear. Here we are. Software. Okay. No, not this one. Let's try another one. Okay. What? Let's use this guy. Now we have to change the equations to correspond to the situations presented on the slides. Okay. So let's see here, degenerate DE. Okay. Degenerate ODE. Degenerate cases for the eigenvalues. Right. Just like this. dx dx. So here we have, for instance, yeah, let's take the first case. So 0 times x1 plus 0 times x2, and the second equation is 0 times x1 plus lambda L2, lambda 2 times x2. Okay, x2. So this is the degenerate equation. This is the degenerate equation. L2 here is, say, let's put a number 2 to it. Okay, and now let's open the simulation. The simulation file and change it. So, not print, sorry. But let's save this guy. Okay. Let's call it like this. T0, T final, whatever. Not P0, but X0, some initial conditions. This is TX ODE45 degenerate ODE, T0, T final, X naught. Relation of degenerate linear systems. Okay, plot TX, title behavior near equilibrium point degenerate cases. Okay, while well, label X. Legend. X2. Okay. And now we have the phase portrait. Phase portrait. Phase portrait. Portrait for the degenerate case. Grid. Y label is X1. And X label is X1 and Y label is X2. Okay? Let's see if this it will be running out to path and see what happens. Well, something's wrong. Something's wrong. Column 22. Oh, this shouldn't be here. What's wrong? L2. Degenerate line 7. Oh, because this is capital L. Sorry about that. Save. No. Save. Something's running. Maybe we'll see some plots. Now you see? You see what happens? This is the degenerate case. Yeah? This is the phase portrait. It's a line because x1 is 0, is constant actually, and yeah, here I gave the initial condition 10. Let's make it 1 here, and you'll see the difference in a minute. Yeah, so you see now it's 1 here. Look, the red line you can see here. The red line you can see here. Okay. phase portrait grid, but it said grid. Why isn't it showing a grid? You see? Look, here it is. You see? X1 is constant and X2 is running. And look, since L2 is an unstable eigenvalue, lambda 2 is unstable. Look here, it's positive. We should, maybe I should do it negative. Okay, so we can see the stable part. Here, you see? X1 is constant, is always 1, and X2 now is stable. And look, this is the phase portrait. It's going to the case 0, 1. 0 for X2 and 1 for X1. You see? You see? This is the equilibrium point. Let's run this again. Yeah, look. Is it clear now? So this is the way from top to bottom. Okay? So this is a degenerate case. Now let's take another degenerate case. Let's take another degenerate case. The next degenerate case, if you look in the slides, is this guy. So L2. Now let's put here A1, 2, like this, or something, or A equal 1, A2 equal 0, L2 equals 0. Okay, save, run. You see, it's changing now. It's changing. Yeah. Look, unstable. X1 is unstable, and this is the horizontal parallel line. Let's see. Maybe we should take this guy to be. Let's see if negative works better, because I would like to see something stable. What's wrong? No, this guy. You see? No. So this is never stable. This is an unstable situation. See? And this is the phase portrait, this parallel line. Okay, X2 equal constant value 10, and X1 is varying. X1 is varying. Okay. So this is a degenerate situation, and the most degenerate situation of all, the mother of all degenerate situation is everything is 0. Everything is 0. Wow. See? Everything is 0. Let's run again. Yeah, degenerate completely. So you see essentially nothing. Nothing. Okay. All right. So this is the most degenerate of all. Now, essentially, what you can do, you can look at the situations. Yeah. So you can do it like this. For instance, you can say here L1, and this is A1, 2. This is A2, 1. And you can have the most general case. L1 and L2 can be looked at as eigenvalues if you take diagonal or non-diagonal stuff. For instance, this is -1, this is -2, just like we had the node, the first case of a node. What we have, A1, 2 is 0, A2, 1 equal 0, and now it's not degenerate. Now it's all the it's all the cases. So you can do this save as equilibrium point linearized behavior. Okay. OD. Okay. And I think we have to use this because MATLAB hates minus, right? Okay, and you call this what? Equilibrium point, linearized behavior ODE. Okay, and you use this piece of text, this guy. Sorry, do this save as. Okay, simulation of the linearized behavior at equilibrium points. In that case, phase portrait for the behavior at equilibrium points. Well, node, you see, stable node. This is a time variation. This is stable because it goes to 0. Very lovely, stable node. You agree? A very lovely, stable node. Let's do a saddle point. Do you want to see a saddle point? I suppose you do. Oh, I should close this. And why don't I use it here? Here. Huh? No, CLF.
You should remove hold on from the bottom.
I should remove the hold on, but I actually wanted to see something using hold on.
Yeah, but
okay, right. Let's just comment on hold on. Fine. Okay, like that. You agree?
yeah.
No. This is a saddle point. It's not so easy to see, but you can see the type of trajectory. It's unstable. It's a saddle point. Okay, it's unstable. You can zoom in if you like. What happened? Oh, pushed help. So you can just zoom in. Do you know how zoom in works? Well, you can just zoom in, but this is a saddle point. You see, look at the configuration. This is a saddle point. And I want to see now. A center. Do you want to see a center? Huh? I suppose you want to see a center. A center. So what do we need for a center? We need 0. We need 0 real part. And that's on the main diagonal. And we need plus and minus. Plus and minus. So here you need -2, and here you need 2. This is for the j omega part. Okay? Now this should be fun. Center. You see? They're both oscillating. They're both oscillating. You see that? This is a center configuration. This is a center configuration. Right. But we can do a perturbation on this center configuration. You agree? Let's see what happens if here we don't have 0. But here we have plus epsilon. Let's define epsilon. Yeah. Equal 1e minus 5. This means 10 to the power minus 5. You understand? epsilon. And now you see the result of the discussion of the argument about perturbations, epsilon, right? Agree? Run, not you, the other one. Well, you cannot see much now. This is too small, so this is considered an error by this guy. So let's make it smaller. I can't see much. I want to show you a perturbation. Why can't I do that? Epsilon. This. Save. Run. You see? It's changing. Look. Look. The amplitude of the oscillation is growing. You see that? So this is not stable because you have this perturbation is changing this into an unstable focus. Okay, let's do it. Let's do it with a minus. With a minus because stable is much nicer, right? You see? Look. So this is going to a stable focus. So this is probably going away slowly. Let's change here final T 700. Ah, this is fun. You see? It's no longer a center. It's no longer a center because things are starting to fade away. Things are starting to fade away. So this is degenerate. Center is not good. Linear oscillations are not structurally stable. Linear oscillations are not robust. Like it? Let's make this one 0. Let's change. I would like to show you a focus now. I'd like to show you a focus. So L1 is, say, 0.5. L2 is 0.5. This is the real part of the eigenvalues. And let's leave it like this. Let's leave it like this. Wow, you like it? This is unstable. Fuck. I want it stable. Sorry about that. Because I like stability. Look, a stable focus. Love it? This is a stable focus. This is a stable focus. Yeah. I think that 700 is a bit too much. So let's make it 100. This is better. Okay? This is much better. Right? So this is a stable focus. This is the pendulum. This is how the pendulum is behaving. This is how the pendulum is. This is too much. Make it 20 or so. Yeah. This is how the pendulum is behaving. Okay. This is the behavior of the pendulum. A stable focus. Okay. What else? So, and now we can see also the double eigenvalue problem. Double eigenvalue. So I need A21 to be 0. A12 should be 1. And these people should be equal. Exactly this case. Run. No, not you. The other one. Run. You see? This is the behavior. I showed it to you earlier. It's a stable behavior. It's a double eigenvalue. It's a double eigenvalue. Okay? It's a double eigenvalue, right? So this is kind of fun, isn't it? So this is in canonical form. Please keep that in mind. I'm showing now canonical forms because, of course, I can show any type of matrices. For instance, you can take 1 here, you can take 2 here, you can take, for instance, this one. This is any matrix. Okay, so now we don't have the canonical form. Okay, this is unstable. Sorry about that. I would like to have a stable one. Yeah, let's have a stable one. What? A stable one. No, I know how to make a stable one. 0, 1. This is a stable one. 2, 1. This is a stable one. Yeah, because I took a canonical. What the hell is this? Oh no, it should be a minus. -1, -2. Sorry about that. -2. 8, 2, 1. No. This is a stable. I'm taking a companion matrix of a polynomial. So this is stable. So you see, this is also a node. Look at it. But this is no longer in canonical coordinates. This is skewed. Now, the eigenvectors are not the imaginary and the real axis. Sorry, they are not the vertical and the horizontal axis, but are these skewed axes. These are the eigenvectors. Okay, they are skewed. The same goes for the what? The complex conjugated ones. Let's change it here. Let's make this one 2. And let's make this one 1. I guess I should get it with complex conjugated eigenvalues. I know how to play with these things, okay? I've got experience. You see, the focus is no longer in canonical coordinates. The focus now is in in other coordinates. In other coordinates, okay? In other coordinates. Right. So this is kind of fun, huh? So the center is not structurally stable. The center is not structurally stable. Okay. I hope this is interesting for you. Let's see now if I could show you some Maple stuff. Show you some Maple stuff, because Maple can also draw very nice phase portraits, and Maple can also implement very easily in symbolic calculations, can easily implement the polar coordinates. Can easily implement the polar coordinates. Let's see if we can see that. We have some examples. These examples are uploaded on internet, on your Moodle. I'm not sure if you noticed, I have put in the file section of your Teams class. I've uploaded a Maple kit. Have you found it?
Yeah.
Did you find it? Lovely. It's very easy to install. You just need to follow the cracking instructions, which are very easy. This is an older version of Maple, so probably no one will care about it any longer, but it's very useful for our practical and for our teaching stuff. Okay? So please try to install Maple and check out these very funny, very nice examples. I have to show you some a little bit. Let's see if it works. So I have them here. I've got them very nicely. Face portrait, yeah. I can already show you. Oh no, the van der Pol oscillator. I want to keep it for the next week. I want to keep the van der Pol oscillator for the next week. But look at this example. We've got here a system of this form. Okay, you see this guy here. R dot is minus 5r times 5r squared plus 1, and theta dot is constant. But this is yeah, you see, this is the phase portrait of this guy. But I didn't want to show you this. I wanted to show you something else. Limit cycle. I don't want to see the limit cycle. Pendulum. You see, this is the pendulum, for instance. This is the pendulum. It got friction. We have friction here. Mass is 2. This is K over M, minus K over M here. Okay? This is the friction. And look, phase portrait. Phase portrait, you see? This guy is the phase portrait. You can compute the phase portrait. There is a special command about this called phase portrait. And here I try to do the phase portrait using plot of the ODE solutions. This is also very nice. And here, these are the time domain solutions. But here, what you can do, you can also implement. I wanted to show you an example where polar coordinates have been implemented. I think they are in the limit cycle parts on the pole. This is the van der Pol oscillator. Look at the equations. You see the van der Pol oscillator goes to a limit cycle, so it goes to a limit cycle. This is unfortunately, this is an unstable limit cycle, but it can go to a stable limit cycle like this, and it can always oscillate. Here there is. I know I've got examples with the implementation of the polar coordinates. Can't find them for the time being. Here. Yeah, polar coordinates, you see. So a maple, if you can see here, has polar coordinates very clearly, very easy to implement, map to basis, and you transform the Cartesian to polar coordinates. Okay, and this is the phase portrait. It looks like a node in polar coordinates. Okay. Oh, no. This is actually a node in Cartesian coordinates, which you can also plot. You can also plot the polar coordinates, and you can also do their own phase portrait. Okay, their own phase portrait. But this is the implementation into phase portrait of the system. The one r cos theta, r sin theta, implemented into this polynomial. This is a polynomial dynamical system. Let's see what else. Another system, also polynomial. You see, you have here a focus. You can run all these things. And then you have maybe this guy. Equilibrium points. Look, very nice. This is a limit cycle. It stops here and it will always circle. So this is a constant oscillation. Look, limit cycle. We are going to talk about limit cycles the next week. And we'll see when limit cycles do exist and when they do not exist. Okay, limit cycles. Okay, I think it's interesting to know when you have a limit cycle or not. But this is you see, this is very interesting. Look at this example. This is a polynomial system. So you would easily say, where the hell is this oscillating? Well, it is oscillating. It is an oscillator. And the van der Pol oscillator is a polynomial system. Okay, so this is a structurally stable oscillator. You see, it starts from like a focus, but it will never go to a constant equilibrium, but to a constant energy area in the phase portrait. Okay, I think this is very interesting, don't you think? Yeah. So you'll have all these examples uploaded. Okay. This is another interesting phase portrait, another polynomial example. Look, this is clearly a limit cycle. Look at this guy. Very nicely. Look, limit cycle, limit cycle. It will always oscillate. Look, no matter how you perturb this guy, it will always oscillate. Okay, but we are going to talk about limit cycles the next time. Okay, I hope you enjoyed these pictures. Let's see it even running. I'm running the maple sheet now, so you'll see this is true. You see, it's running, so it's for real. It's for real. Let's shut this down. Let's go back to Teams and let's share the other screen with Can you see the other screen now?
Yeah.
Okay, nice. Good. So we were talking about this, the perturbation of the eigenvalues, okay? And that some of them are structurally stable, okay? And some of them are not structurally stable. So these people, these eigenvalues here on this part, okay, they are structurally stable because no matter how you perturb them, they stay there. But these on the imaginary axis, they do not stay on the imaginary axis any longer. Okay, they just can go to the left or to the right. Okay, so if A has purely imaginary eigenvalues, an infinitesimally small perturbation will push them out of the imaginary axis. For instance, one to the left and the other one to the right, which may be the usual case. Okay, so if the equilibrium point of the original system x dot is ax is a node, a saddle point, or a focus, then the equilibrium point will be of the same type for the perturbed system for any sufficiently small perturbations. These are called structurally stable. So the structure is stable, yeah? Structurally stable equilibrium points because they keep their shape and their properties even when subject to small perturbations or small disturbances. Okay, and we have two examples. For instance, we have this matrix, and we consider the structured perturbations of this type, the ones I showed you with epsilon or delta. Okay, in this case, 0 is the center. Okay, but it becomes a stable or unstable focus, just like I showed you very nicely in MATLAB, when you have this type of structured perturbation. A second problem, which I might leave you to it for yourselves to find out the answer, is you have to determine the largest eigenvalue, absolute value of alpha, for which this system is stable. Okay, this is not a very easy problem to do numerically. Theoretically, it can be done. Determine the values of alpha for which 0 is a stable focus for the system x dot is ax. Okay. All right. You can look at these things yourselves. You can try to do this as a homework. Number 2. Try to investigate it as a homework. Okay. Now we looked at the linear object. The linear object, but the linear object is not the nonlinear object. It's different from that. It's someone else. So let's go back to the nonlinear system and see what conclusions can we draw, or what conclusions we can draw from the behavior of the linearized variational system. Okay. So this system psi dot is xi plus is equivalent in some sense to the initial system. It's equivalent, but it is equivalent when you add these higher order terms. When you don't have the higher order terms, this guy is a different object. Okay, this guy is a different object. Okay, so linearization means that small terms O xi of higher order higher than 2 usually are neglected because the variations are very, very, very small. Hence, one can assume that in a sufficiently small neighborhood of the equilibrium point or the origin, okay, these terms are arbitrarily small. Okay. So under these circumstances, taking into account the remarks about the linear perturbed system, one can prove rigorously, it's very interesting, that in a sufficiently small neighborhood of the equilibrium point, the trajectories of the nonlinear system are arbitrarily close to the trajectory of the linearized guy. So that's why we study the linearized guy, because now you can consider these higher order terms, you can consider them as delta A. They are similar to delta A. That's the explanation for this. This is the explanation for this. You may view, okay, you may take into account the higher order terms as a structured perturbation applied to the matrix A, okay? Oh crap. All right. Okay? Fine. So that's why we study the linearized guy, because the nonlinear guy can be considered for very small variations as a perturbation version of the linearized guy. Okay, an approximation. The linearized guy plus higher order terms is an approximation of the nonlinear guy. Okay, so we can understand what's going on. Okay, so this property, they say here in general, holds for structurally stable points: node, saddle point, or focus. So when you have this type of points, things are similar. When you have center, things are not very clear, are not so similar. Okay. Well, in conclusion, the qualitative analysis of the behavior of a nonlinear system around the equilibria can be done linearizing the system in the neighborhood of each equilibrium. True. The type of equilibrium of the nonlinear system can be assimilated, well, with the type of equilibrium into the origin of the linearized system, okay? Provided the origin is a structurally stable point. Well, I say we should stop. It's enough for today. If you have any questions or comments or remarks, please.
I don't have any questions, but I like the simulations.
Right, you can do them yourself. I'm going to upload these files on the Teams class. You can download and play with it, and if you can improve the code, please do so. Okay? Because probably for code you are much better than I am. Okay? Well, I'll try to see you next week.
Okay, thank you. Have a nice evening.
You too.
Thank you. Have a nice evening.